even setting it up beforehand. And let me take you to the practice quiz. Problem 1. So T is the time in years, F of T is the price of oak in dollars per cubic foot. Your company makes oak chairs, so you keep careful track of the price of oak. F prime of 2020 is 4.3. Interpret this with a complete sentence. Make the sentence as specific as possible and as easy to understand as possible. For the most of it, try to have it so that a third grader could understand what you're writing. You use words like, I don't know, any of the technical words, explain instead of using those words.
Did you start the recording yet?
I did. Thank you for checking. So when you get into Discord, before I'm in Discord, get into the voice channel right away. And that way, when I first get in myself, you'll be able to hear me, because I often start talking right off the bat as soon as I get in there. Okay, 30 seconds more. Okay, if the original problem had said not f prime, but f of 2020 equals 4.3, then the interpretation would have been in 2020, the price of oak is $4 and 30 cents per cubic foot. But this is not what this is saying, because we didn't say this. We said f prime of 2020 is 4.3. What this means is the slope is 4.3. But if you just write the slope in 2020 is 4.3, no way a third grader can understand that. So we need to describe what that means. From 2020, 2021, the price of oak will increase by $4.30 per cubic foot. And then the last part of it, the third grader wouldn't understand, but I'll put it in there. Provided we stay on the tangent line. Now, situations are often very flexible and things change quickly, and often you don't stay on the tangent line. But absence of any other information, that's usually our best guess into the future. If we at least know the tangent line, we project along that. All right, give me a little feedback on this. You don't have to say nailed it or not. I decided that's not really important. But give me information about whether the review is helpful or not. And type that up. Don't hit enter quite yet. And go ahead and hit enter. Alright, let's go to number 2. Let me get a little bit larger. Do that integral. Okay, I'm not going to give you time to do the whole thing, but at least get the setup. Get a few things going. I'm going to give you one more minute. Okay, so when we were doing this on Monday, I was jumping right into use substitution right away, and Kylie suggested we change it to the correct form right away, and I agree with that idea, so I'm going to do that over here. I'm going to break this up. We've got to go as two separate integrals. It's not allowed to go from negative infinity to infinity. I can pick any number in between. I'm just going to pick 0. I could have picked 1 or 2 or anything like this. So it's got to be broken up into two separate integrals. And now if this had been like e to the x squared over 1 plus e to the x squared, and I knew that it would be symmetric with respect to the x-axis, I would have just put 2 times the integral from 0 to infinity. But this is actually a different looking function to the left of the y-axis and to the right of the y-axis. But you see here, it wouldn't matter whether x was positive or negative on this. So we do both. We got to do both of these, and then we're going to change each of those into limits. Limit as t approaches negative infinity from t to 0. Plus the limit, and we can do t again, it doesn't matter. As t approaches positive infinity, 0 to t. And then now we're going to need the u substitution. It'll be the same u substitution for both. So I'll let u, it seems natural to let the u be e to the, either e to the 6x or e to the 3x. But if I do e to the 3x, the e to the 3x will be the du, and I need that to be the du. So this really needs to be 3x. And then du dx, but I won't write the dx, I'll bring that to the other side, will be the derivative of this, which is itself, times an extra 3 dx. So, and by the way, notice that if I square the u, I get e to the 3x squared, but power to a power you multiply e to the 6x. So that'll take care of that thing at the bottom. And then, so e to the 3x dx is 1/3 du. Alright, so then we can do each one of these limits equals, and I'm going to leave the rest. You got to do two things here. But this is what I really wanted to focus on here is the setup and getting going on this. And give me a little feedback on number 2. Go ahead and type that in. Don't hit enter quite yet. And go ahead and hit enter. Rowan is asking that I solve it completely. Who agrees with that? Wants me to keep going? Yes, alright. Let me finish it out. So, let me get some more space. So then this is a limit as t approaches negative infinity, integral from t to 0 of And we get this almost the same thing in both cases. On the top, well, in the bottom it's 1 plus u squared. And then the top, it becomes du. The e to the 3x dx all becomes 1/3 du, and I'm going to put that 1/3 way out here. Okay. And then, so then this is plus, and then the same thing is going to happen, but it's a limit. As t approaches infinity, of 0 to t, du over 1 plus u squared, and again it's got a 1/3 squeezed in here. Okay. And then we've got, now when I take this integral of 1 plus u squared, I look it up in the back of the book. There's no u up here, so it's not like let w equal u squared, and then so it's not set up for u substitution. We got to use one of these. This one I kind of have enough experience to know. I can look in the formulas with the x squared and a squared, but I'm not going to find it there. That's 76 through 85. And when I don't find it there, I know look back at 13 and 14, right around there. And this is rule number 13. So I'm going to use rule 13. So this is 1/3. Limit as t approaches negative infinity. And when I do this, rule 13, so the a is 1 and the x is u, and so this becomes 1 over a, which is 1 over 1, times the inverse tangent of x, which is u, over a, which is 1, and this, it's evaluated from t to 0, plus 1/3 limit as t approaches infinity, and we do the same thing. We're going to get the inverse tangent of u. Now, these were x's, by the way. Let me emphasize that with red. X equals. When we get down to here, we probably need to be changing this to make it go quicker. Let's make these u equals. So u is equal to e to the 3x. When we substitute t in, we're going to get u equals e to the 3t, and u equals e to the 0, which is 1. Okay. And then this one is from u equals e to the 0, which is 1, to u equals e to the 3t. And when I substitute them in, third limit as t approaches negative infinity, I'm going to get the inverse tangent of 1 minus the inverse tangent of e to the 3t plus 1/3, substitute these in, inverse tangent of e to the 3t minus inverse tangent of 1. Now, make sure your calculator's in radian mode, and you can punch in inverse tangent of 1. But you'll get it as decimal, and you might not recognize what it is. If I just draw a little tiny unit circle, sine and cosine are going to be the same right here. That's when you're going to get tangent of 1, and that's pi over 4. So this is equal to, these are pi over 4. 1/3. Now, so this as t goes to negative infinity, you're going to get the inverse tangent of really, really, really big e to really, really big negative numbers, which when t goes to negative infinity, this thing will go to 1 over e to really huge, which means it goes to 0. So you're going to be taking the inverse tangent of 0. So now remember, tangent is sine over cosine. When is the sine 0? It's over here. Down here. So which is 0. So this whole thing is going to be going towards zero. And this one, oh, I forgot this limit. We're going to have the limit as t goes to infinity. Now, as t goes to infinity, you get the inverse tangent of huge, huge numbers. And if we just take, and make sure that I'm going to make my mode, make sure that it's radian, and it is on my calculator. I'm going to take the inverse tangent of a really giant number, one with a whole bunch of zeros. And when I hit enter, I get 1.57, which is really close to pi over 2. So this goes to pi over 2. And that's because when the tangent is huge is when cosine, because it's sine over cosine, when cosine is almost 0. And cosine becomes 0 at pi over 2, so that's why we're over here, pi over 2. So then this becomes 1/3 times pi over 4 minus 0 plus 1/3 pi over 2 minus pi over 4, and then this becomes equal to pi over 12. When I take this, pi over 2 minus pi over 4 is pi over 4. It's 2 pi over 4 minus 1 pi over 4 is pi over 4. So this is pi over 12 plus I get another pi over 12, which is pi over 6. That's my final answer. Alright, so now let's go to number 3. State the formula for the length of a curve. Y equals f of x, from x equals a to x over b. So it's just from memory, the length of the curve formula. Thirty seconds more. L equals the integral a to b square root 1 plus prime of x squared dx. Give me a little feedback on number 3, length of formula curve. Go ahead and hit enter. All right, remember to okay, and when you skip some little part of it, you'll probably remember it next time because it'll stand out more. Alright, and alright, that's it for practice quiz for today. Let me flip today. Let's do 9.1 first, and then we'll go to answering questions on homework problems. And 9.1. Chapter 9 is about differential equations. And differential equations, if you're going into an applied science field, like for instance in engineering, it's very typical after you take the calculus sequence, Calc 1, 2, 3, the very next class that you might be taking then would be a class on differential equations. And what differential equations are. And this is one of my favorite topics in this class. All right. So a differential equation is an equation that involves an unknown function f and some of its derivatives. And what's unusual about differential equations is that a solution of a differential equation is a function. We're not used to solutions of equations being functions. We're used to solutions, 4 is a solution, or 10 is a solution. Or maybe if it gets abstract, it has a constant in it. But that the solution is a function is really different. Now, in all the classes that you've had up until this point, you may have had application problems that have felt kind of like, they're kind of contrived. They're not really useful. They wouldn't help me do any real problems in the real world. And there's an extent to which you're correct in that, because real world problems are more complex than the kind of simple equations that we can solve in algebra classes. Real world problems, often when we model real things, we often get a differential equation. And they're much more difficult to solve. But finally, you're going to be getting to those. How do you solve differential equations? And eventually, you may get to classes where you set up the differential equations. You model situations with differential equations. So many scientists, when they model situations on computers and then have the computers, find out the solutions, typically they're setting up differential equations. And what a chemist and a biologist and so on, the difference between them and a mathematician, though, would be that the chemist and the biologist, they just set up the differential equation and then they turn to software to say, okay, now let the computer solve this. They don't want to mess around with how do you solve the equation. From a math point of view, we find the equations themselves very interesting, and all we're going to do in this chapter, though, is get some real fundamental basics of what can be done and how differential equations kind of work. All right, so I'm going to be calling on some groups today, and I want to just check in with the groups again real quick, since that will be a significant part of today. We have 7 different groups. Group leaders, make sure you know who is the spokesman for the day. And let me just run through and tell me, and everybody go into your group chat and type hi, so we know how many's in each group. Group 1, how many of you are there today? Anybody from group 1? Okay. Group 2.
So far it's me, Tony, and Herman, just the two of us.
So 3 altogether, right?
2.
2. Okay. 2 in group 2. And Dominic, are you in group 1? Are you the only one in group 1? And you are, but you have no mic. All right, let me have you join group 2 for today. So unmute your channel 2 and participate and say hi in that group so they know who you are. And group 3, how many of you?
It looks like we have 4 here.
4. Group 4. How many in group 4? And group 5?
There's 3 of us here.
Group 6?
There's 2 of us here.
And group 7?
There's 3 of us.
3 of you. Okay. And all right. So does somebody?
Sorry for the interrupt. The group 4 have 2 people. The other one don't have mic. I'm the only one speak.
Okay. So group 4, I'm going to have you join group 6 today. So unmute the channel for 6. So there'll be no group 1 and no group 4 today. All right. And all right, let's go back to here. Problem A. The problem is the derivative of a function f, df dx, is equal to f. Now another way that this can be put is f prime is f. So this is a function whose derivative is itself. When you take the derivative, you get the function right back. All right, so part 1 is to find a solution to this. So let me give you a moment to think about this on your own. You can type your answer into your group chat, but don't hit enter quite yet. Just see if you can think of a function. When you take its derivative, you get itself. Okay, and go ahead and hit enter. Enter that into your group chat. Then you can discuss it briefly. Excuse me. Okay, group 7. Did you find a solution? What's a function whose derivative is itself?
E to the x.
F of x is e to the x.
E to the x.
Like that, right? E to the x.
Yeah. Yeah.
Okay. Now, does everybody agree with this? This seems clear to me too. When you take its derivative, you get itself. It's not any kind of polynomial function. If you take like x to the 4th, its derivative is 1 degree lower, you don't get itself. There's no way it can be something like a polynomial. But e to the x z. Okay, now that's a solution. Now part 2, find the general solution. Now, remember like when we took integrals? We would say an integral of x squared is x cubed over 3. But a general solution would be x cubed over 3 plus a constant c. You know, because it could be something more than just x cubed over 3. All right, so in this case, find the general solution. So let me give you a little bit of time. And when you think of one, check it out. As soon as you think, oh, I think this is it, check. Make sure it really works. Okay, go ahead and hit enter. Discuss it in your group. All right, group 2. What's a general solution?
So one person put y equals a e to the x. I put that I don't really understand what we mean by the
You're not
general
sure
solution.
what it means.
I'm not sure. Yeah, so
Okay.
maybe pass. I don't know.
All right, so you have a proposed answer and a pass. Okay, and let me ask, did anybody try this? F of x equal e to the x plus c. Maybe that one is a general solution. All right. Now, how do we tell if the general solution is really a solution? What we do is we plug it back in to this. So the right hand side is going to be a e to the x. We plug it in. The left hand side is we got to plug in the derivative. So we check. We're going to need f prime of x. If f of x is a e to the x, f prime of x, well, it's just still a e to the x. And over here, if we have this one, if we take its derivative, what do I get? E to the x, and the derivative of c is 0, so it's just e to the x. So I'm going to write this equation. We're going to check. We're going to ask, does df dx equal f? Well, if this was a complicated equation, you'd have to kind of refer back to here and throw this in for this. And throw this thing in for this. And then say, does it turn out to be a true statement? But this one, we can just look and say, are they exactly the same? And this one, it's yes. So it checks. On this one, does the derivative and the original function, do they match? Df dx, does it equal to f? And the answer is no. One of them you get a plus c, and the other you don't get any c at all. This is not a general solution. You can't generalize the solution like you can with integrals by just adding a plus c. You had to add your constant in front. Now you put an a there, you could have put a c there, it didn't matter, any letter like that. Usually early letters in the alphabet mean a constant. So any early letter in the alphabet would have been fine. All right. Is there any questions on this, or does this seem perfectly clear? I'm going to assume it's perfectly clear unless I get somebody raising a question. All right. Let's go to part B. So, dy dt is ky. Now, oftentimes y is a function of t because in differential equations it's a really common situation that the independent variable is time. So y is a function of t instead of x. It's very often used. And you're going to get dy dt is equal to ky. Find a solution. Go ahead and enter your solution into your group chat. Discuss it briefly. All right, group 5. Do you have a solution?
So we don't know. We're not sure.
Want to pass?
Yes.
Okay. Where a function is itself, but it also has a constant times it up front. Let me go to group 3. Got any ideas?
Someone from my group suggested ae to the bx or ax. Like, yeah.
Okay. I'm going to ignore the a part. I'm going to put the e to the b. Oh, not x, but t this time.
Oh, yeah, sorry.
b, t. All right. Now, is this really a solution? Now, if we wanted this to match exactly this, we could put a k up here. But even if you don't put a k up here, we can kind of see. If we take the derivative, dy dt, what are we going to get? The same thing back. And then times the derivative, the chain rule, derivative of bt, which is b, right here. So you're going to get the same thing back, but a multiple of it. So this really does look like it's a solution. Now, you had suggested, and what's your name?
This is Rowan.
Rowan. Rowan, you'd suggested a e to the b t, and if you're going to put another constant in here, that might be the, and let's do it this way this time. Let me put a k right here so it matches up to make it really clear, where the k is going to be showing up here. Then y prime is equal to, a just comes along, you get e to the kt again, and then times the derivative of kt, which is k. But actually, the way that I really like to see this is I'd put the k out front, and then a e to the kt. Now it's really clear that this part is y. So now you're getting y prime is k times y, this is the general solution of this differential equation. All right, so we've done a couple of these. Give me a little feedback. Do you feel kind of mostly lost? Makes a lot of sense, or it's bending your mind in a new way? Give me just some kind of general feedback. And go ahead and hit enter. If everybody could give me a little feedback, that'd be good. Okay. All right. This is an interesting comment from Kylie. Not sure how it's going to apply to homework. All right. So there's going to be a number of different kind of homework problems. But having multiple perspectives on this will be just one of a number of perspectives. But there'll be one perspective that's a really good foundational perspective. Might not help you actually do a whole bunch of the homework problems, right? But it will give you a better sense of like, oh, I understand this topic. And all right, let's go to C. I'm going to ask for a solution and a general solution. Now we're looking for a function whose second derivative is the negative of itself. It's exactly the same as its original, but opposite sign. Function whose second derivative is the negative of itself. And you may have to take some wild stabs in the dark here. And go ahead and hit enter if you have an idea. Put it into your group chat. When I get an answer to a tough one like this, that somebody has the correct answer right away, I'm usually disappointed because it's like, I'd like to work my way slowly to the answer, and people usually understand it better that way. Let me give you another 30 seconds here. All right, group 6. Can you think of any function? When you take its second derivative, you get the negative of itself.
We had somebody say that they thought it was sine x.
Sine x. We're going to check that out in a minute. Well, before we check that out, let's check this one out. I had people suggest it was, I remember from previous classes, like, not a K, but an X or a T. Those are the typical ones. If I take y prime, I would get negative 3e to the negative 3x. And if I take y prime prime, I get another negative 3 multiplying by it. And then they say, well, look at this. It's not the same. It's an extra constant. So maybe if it was just 1 instead of 3, maybe it would work. Maybe if it was y to the e to the negative x, then y prime would be negative e to the negative x, y prime prime, oh, but a negative times another negative is back to positive. And this is, even if it's a negative exponent, negative 1, you don't get it to be negative of itself. It winds up being the same as itself, because that negative gets multiplied in there twice. So you need something, not like this or this. We need something crazy like this. And let's watch. The derivative of sine is cosine. And the derivative of cosine is negative sine x. But that is negative y. Y prime prime is negative y, and it checks. Alright, so sine works. Alright, let's go to the next part. Find a general solution. And let me warn you, the general solution for this one is not easy. Let me give you a minute on that. And go ahead and use your chat group. "30 seconds more. And let's go to group 3. Do you have a possibility for a general solution?
We don't have a general solution, but I think we perhaps think that cosine might also work as a solution.
Let's check it out. Y equals cosine x. Y prime. Derivative of cosine is negative sine x. Y prime prime. The derivative of sine is cosine. Yes. Cosine works just as good as sine. Alright, so let me open the floor to anybody. General solution.
Can we do the a sine x?
Very good. And there's more to it though.
You could also say plus or minus.
What?
So just like, you could either have a times the sine of x or negative a times the sine of x.
That's right. A could be positive or negative. But
Plus b cosine of x.
very good. You could
Is
have
it a
different
function? Is this? I know this is a function. I can't remember what it's called.
I'm not sure what you're talking about.
It's a trig function, I think.
That is when you add the sine and the cosine together.
It's specific though. We learned it last class.
Okay. All right. Well, let's check this one out though. See if this really is the general solution. If it is, when I take the second derivative, I should get back to y. When I take the first derivative, the derivative of a sine x is a cosine x. Derivative of b cosine x is minus b sine x. And the second derivative, Derivative of this cosine is negative sine. Derivative of sine is cosine. And if you factor out a negative, and that's equal to negative y. And it checks. That's the general solution for this one. And what we're going to find out with differential equations is that we have an order. When it's the first derivative that's involved, it's called a first order differential equation. If there's a second derivative involved, it's a second order differential equation. And if the highest derivative is to the first power, first order differential equation, you're only going to get one arbitrary constant. If the highest derivative is 2, second derivative, second order differential equation, you're going to get 2 arbitrary constants. And if it's a third degree differential equation, y prime prime prime, you'd get 3 arbitrary constants, and so on. The number of arbitrary constants is going to be the same as the order or the highest derivative in your differential equation. All right, we have more of these to look at, but well, let's do one more, and then we'll take a break. So, dy dt is negative ky. So, it's a function whose derivative, first derivative is itself, but negative. And it's got a constant k in it. Now when you find a solution, you might pick a particular number for k if you want. Like 2 or 3 or 4 or something like that. That'd be fine. Okay, and let me give you a minute more. Discuss it with the group. All right, group 7. Do you have a possible solution?
I said f of x equals e to the negative 3x.
Let's check it out. So then y prime would be negative 3 e to the negative 3x, and the k in this case you're using as 3, and so then you're going to get this negative extra sign over here. So if we generalize that to y equals e to the negative kx, then y prime would be negative k e to the negative kx. Now, let's see if this matches up with this. The negative k times e to the negative kx, but e to the negative kx was the y itself. So you're getting y prime is equal to negative k y. So this checks. And then the general solution, group 7. Do you have something for that? Group 7. I think it's going to be just putting any constant a.
Yeah, I was gonna say it would just be f of x equals ae to the negative kx.
Yep, and that would work for this. All right, so let's stop here, take a 15-minute break. We will start again at 6:47 p.m. Does anybody need to talk to me about anything before I take my break? Okay.
Mr. Shankin,
Yes.
I do have. Hello.
Yes.
I didn't submit my work today for
Spot check?
8.9. Yes, spot check, because I don't understand. So I need few more time to understand the class. I need time to read the book. So I didn't submit the spot check.
I'll give you a special extension. Just email it to me.
Okay, thank
and
you.
I'll let you have that one. Because if
Thank
there's
you.
something occasionally like that happens, you can just let me know. Yep. All right.
Thank you.
You're welcome. Yeah.
How do you get your food all organized when you're camping? And she's a foodie.
Yeah.
She used to have a restaurant and a bakery in Silver City. And she said, when she goes down to her restaurant, a bakery for some reason, and she was moving things, that's sad for himself. A teacher that quit, got to live basically camping. She got to live. And she's super close to her son. She and her son, she said, my son, I just don't well, he's probably my age.
Okay.
Because she's almost 70.
Wow. Okay, I'm going to start again. All right, we shall start again here. And all right, next one. dy. Now I can't mix up my t's and my x's. Let's make this dy dx is equal to x squared. Find a solution, find the general solution. I'll give you a minute to work on this individually. Okay, enter it into your group chat. And group 6, do you have a solution?
We're gonna have to pass.
Okay. And let me go to group 5. Do you have a solution?
We have 1/3 x to the third.
Well, let's check that out. If I take its derivative, I get x squared. So that checks. So that's my solution. And what's your general solution? Group 5.
Didn't get that far.
Could
Okay.
Oh.
Anybody?
Could it be something like 1 over a and then x to the power of a?
1 over a, x to the a. Well, let's see. The a's would cancel out, and you'd get x to the a minus 1. But that would only work if the a was 3. So no, we can't. It's a good idea to generalize it that way, but it won't do it. Anybody else have another idea? General solution.
Can we try natural log?
Natural log.
Because it's ln of whatever.
So dy dx would be 1 over x, but y dx has got to turn out to be x squared. So that one doesn't work either. Okay, what else? A general solution.
Can we do the a plus 1 instead of just a?
A plus 1, even if you did, you got to get specifically x squared as a result. And so if a was like 5, you're going to get x to the 4th as your derivative. So even you can't do the a, you can't turn the a. The exponent has got to be a specific number. Well, let me give you the answer. That's it. Because when you take its derivative, you get x squared, and the derivative of a constant is 0. So this is the general solution. Right here, and that checks it out. All right, now, when you have a situation like this, how is this different than all the previous problems? All the previous problems had the output variable, the y, in its solution. Every single one of those. This one just has the input variable in it. And all we really are doing over here is we're integrating both sides. Integrate this side, integrate this side. And then you also multiply both sides by dx. When you multiply this side by dx, the dx goes away. And when you multiply with this side, you get dx over here. And then the integral of dy, these two kill each other off, and you get y equals 1/3 x cubed plus a constant c. Now, technically speaking, E is not a differential equation. It's not hard enough. A differential equation is an equation that involves an unknown function and some of its derivatives. So if it was y or f, it would have to have y or y prime as its in there. So we could say, though, we could kind of loosely say that the left-hand side, where were we at? The left-hand side had its derivative of y. So in that sense, then, we could say, yeah, this is a differential equation because it involves y prime. Right over here. But it's a really much simpler differential equation because all we have to do is integrate both sides if the only thing on the right-hand side is the input variable. If it has the output variable in it too, then integrating both sides isn't going to work. If you tried integrating both sides on D, you just get a problem. You'd multiply both sides by dt, and you would get y's and t's over here, and you can't integrate this. This would be y, but this would be unintegratable. And so differential equations are harder. A real differential equation is hard. We might call this kind of a trivial differential equation, not nearly so difficult when it just has the independent variable. All right. Now, part F, dy dt is equal to y plus 2. So this one is a function whose derivative is a multiple, not is a multiple of itself, is itself plus 2. Okay, so find a solution and then a general solution. Consult with your group. I'll give you just a minute more. Group 2, any ideas? A possible guess that might work.
How about x times y plus 2?
X times y, say that again.
X times y plus 2.
Okay, now, I'm glad you put this. You suggested this, because this will clarify something for us. When we have a solution, we want the solution in the form y equals just the independent variable over here. We don't want the dependent variable again showing up, because then we don't really know what the y is as a function of the independent variable. Is it an exponential function, a linear function? We can't tell. So, thank you very much for doing that. That really makes that point, is we gotta have this. Now, also, we know that the independent variable is t, because it's dy dt. So instead of x, let's use a t. We can't have this y over here. And I'm going to try something. I'm going to put e to the t. And I'm going to also do something else. I'm going to try this. I don't know if it'll work. I'm going to put minus 2. Now here's my thinking. E to the t is something that when I take its derivative, I get itself. And then if I had a minus 2, then maybe when I do the plus 2, that'll give me back. All right. So let's check, see if this is. Now, when you have a more complex one, what we're going to do is we're going to take dy dt right underneath it. Take the derivative of the right-hand side, and I just get e to the t, the derivative of 2 is 0. Now my check, I'm going to rewrite the original. I'm going to substitute e to the t for dy dt. I'm going to substitute, I'm going to put a question mark. For the y, I'm going to put e to the t plus 2. So that's this y. No, e to the t minus 2. plus 2, and dy dt, is it the original y plus 2? Plus 2 and the minus 2 cancel each other out. And does this thing check? Does this seem valid to y'all? This check. Is this y really a function whose derivative is itself plus 2? Yeah, it seems to work over here. And then I'm going to skip this, the general solution, for now, because this is kind of complex here. Y equals e to the t. I'm going to double check this a second. Y is e to the t minus 2. When I take its derivative, I get this. When I rewrite my original, I get that, and plus 2, and then I get, that seems to check. So that would tend to say that it's a solution. Alright, let's move from there to what we call initial value problems. The solution of a differential equation will involve some arbitrary constants, unless you were also given initial conditions. So let's look at this first one. Y prime is equal to 3 plus e to the 2t. Now, this one, can I solve for y? Well, I can do this directly. This is like this easy problem. It's not like any of our tougher ones where the y showed up on the right hand side. This one, the independent variable is the only thing that shows up over here. So I can integrate both sides. And what I get, when I integrate the left hand side, I just get y. When I integrate the right hand side, I get 3t plus e to the 2t again, but I'm going to have a 1/2 in front of it. Because remember, when I take the derivative of this, it has to check to be this. So technically speaking, to integrate it, I'm supposed to do a u substitution, but I can just guess and get this. And then also, there's a plus c. Solving a differential equation, now this is a simple type of differential equation, introduces an initial condition. Introduces an arbitrary constant. Alright, now, if you had this one, it's the same problem, but you also have what's called an initial condition. Then we would get the same solution but now we substitute, that's the t, and that's the y. So y equals 3 times 0 plus 1/2 e to the 0 plus c. And then this becomes 5 equal, e to the 0 is 1, and this is 0. So you're going to get 1/2 plus c, where c is equal to 4.5. So then the total solution if it's what we call an initial value problem, if it has an initial condition with it, the solution will be this function and replace the c with 4.5. And then we've got it. So, once again, you'll have arbitrary constants when you solve a differential equation, unless you're also given an initial condition. Any questions? Okay, let's move on. Let's do this one. So on CC, this also is the easy kind, but you're going to have to integrate twice. So let me give everybody a minute to work on this and work on it independently, and when I tell you, then enter your answer into your group channel. Okay, and see if your answers are agreeing with mine. When I integrate once, I'm going to get y prime on the left. It'll take away one of the derivatives. I'll get 12x squared over 2 minus 20x to the 4th over 4 plus a constant. Now, this is going to reduce 6x squared minus 5x4 plus a constant. Now we're going to integrate again. And then the y prime will just turn into y. And let me get more space here. And I get 6x cubed over 3 minus 5x to the 5th over 5. Now, when I integrate this, I get plus cx, so that its derivative is c. But when I integrate again, the second time, I introduce another new arbitrary constant. So I should put plus c. But if I put plus c, that implies these two are the same constant. So when there's two different constants, we start using subscripts. And then a new arbitrary constant comes up like this. So then this would say y is equal to 2x cubed minus x to the 5th plus c1x plus c2. So when you solve a second degree differential equation, you get two arbitrary constants, because the simplest way to look at it is if it's only just got the independent variable over here, you just integrate twice, and each time you integrate, you introduce an arbitrary constant. But even if this was a really complex differential equation, and it had y's over here as well, still you're going to get two constants coming out of a second order differential equation. Thus, an initial value problem like this is never given. If it's solve a second order differential equation, you have to be given two arbitrary, two initial conditions. And if the independent variable, often it's time, and a very common thing is they tell you the initial position and the initial velocity, something like this. So I'll tell you y at 0 and y prime at 0. That would be an initial condition for this problem. So if this was the case, see, we're getting it to here. Well, no, I said 0 on this one. So if we solved this one, the best you could do is get one of the constants. So they don't actually do this, but let me just show you what would be the case. This is the x, this is the y. So we take this solution up here and we would bring it all down. And the y would be 1 on this side. The x's would all be zeros. When x is 0, it zeroes out everything except, so it's 0 minus 0 plus 0 plus C2. And this would tell you what C2 is. But it wouldn't tell you what C1 is. So when you have a second order initial value problem, it will have both of these. So then you can if y0 equals 1, telling you C2 is equal to 1, y prime of 0 is equal to 1, what we do then is we go back to our solution. We know now that the solution so far is, we know that C2 is 1, so I'm going to rewrite this equation by substitute 1 for C2. Oops, it's supposed to be a 3. Okay, now we know that y prime of 0, where'd that go? Yeah. Y prime of 0 is equal to 0 as well. Okay, so when we put this in, we're going to, first of all, take y prime. We think about y prime as 6x squared minus 5x to the fourth plus c1, and that one disappears. Now, into this equation, when the x is this, the y prime will be that. So we plug those in. 0, and then all the x's become 0. So this tells us that C1 is equal to 0. So then my total solution is this equation that's in blue, but replace the C1 with 0. That's the solution of this, initial value problem. All right. Now, the homework problems that you're going to be doing in 9.1, they're going to be the easy type, where it's just the independent variable over here. And so, it's just trying to get you used to you're going to get 2 arbitrary constants, and then you're going to find those arbitrary constants one at a time. And you're also going to be verifying solutions. And we've already been doing this so far, but let's go into it a little more in detail. It asks, is y, which is equal to e raised to the 1 over 4t to the 4th power, a solution to this differential equation? How do I tell if that's a solution? So let me write this again, because this is a little bit hard to see. 1 over 4t to the 4th. It's like this. So then y prime is equal to, when I take the derivative of this, I get itself I'm going to write it like this though. Because I have to use the chain rule and take the derivative of this. When I take the derivative of this, the 4's will cancel. I'll get negative t to the negative 5. Okay, and then that becomes negative c t to the negative 5 e to the 1/4 t to the negative 4. All right, so now I have y and y prime figured out. Is this a solution to this differential equation? Well, what I do is I take this differential equation and I rewrite it, but I substitute. When I see y prime, I'm going to put this. When I see y, I'm going to put this, and see if this turns out to be 0. So y prime becomes negative c t to the minus 5, e to all this stuff, plus 1 over t to the 5th times the y, which is c e to the 1/4 t to the negative 4. And does this equal 0? And will it equal 0? Well, yes, because this and this are exactly the same. One's positive and one's negative. So yes. And so that verifies this is a solution. Alright. So let's just make sure you have it down. go ahead and verify that this is a solution to that differential equation. I'm going to give you a minute to do that. Okay, so what I have to do is take y prime, which is 5c1 t to the 4th minus 4c2 t to the negative 5 minus 3t squared. And there's no y prime over here, but I had to go through y prime to get to y double prime. And multiply this down, that's 20 c1 t to the 3rd, negative times negative is plus 20 c2 t to the negative 6 minus 6t. And then I take this equation here and I rewrite it, but t squared times y prime prime. But the y prime prime is this. Then minus 20 times the y, but the y is this. Equals 14t cubed.
Mr. Shankin,
Yes.
it says 20 times y, but the function for y is c1 times t to the 5th plus c2.
Oh, thank you, thank you. I was using y prime, wasn't I? I would have been wondering why it's not balancing out. Okay, and then this is equal to 14t cubed. And we're wondering, does it equal 14t cubed? If it does, then we have verified. And so now I distribute this t squared over here, and I'm going to get 20 c1 t to the 5th, and so forth. does that equal 14t cubed? And then we notice this and this cancel out. We notice this and this cancel out. And then we just have 20t cubed minus 6t cubed, which is 14t cubed. And it does equal 14t cubed. It checks. We verified our solution. All right, that's it for this section, 9.1, differential equations, basic ideas. And are there any questions dealing with this section? And then if there's no more questions on this section, we can go to questions on any homework or prior problems. All right. So anything in 9.1 though that needs clearing up first? Okay, let's go to any other questions. Any previous homework problems? Anything else? So on 8.7 we have a few, starting with number 15. Let's see in my book. Right. One note is acting up. I'm going to have to close it out, open it up again. Alright, so let's go. Eight point 7, 15. The integral of x over the square root of 4x plus 1 dx. Alright, in this I try to look up a table entry in the back of the book to see if that takes care of this problem. And do I see any table entries in the back that are just like this?
Yes, it's R94.
94. Yes. So I would use rule number 94.
Tristan said he meant 8.9.
8.9. Ah.
Yeah, he said sorry.
8.9, number 15. Find it. Okay. This is very much like our practice quiz problem. Negative infinity to infinity of dx over x squared plus 100. And let's go look at the practice quiz problem. This one. it became this integral from negative infinity to infinity of a u squared plus a 1, which is really the same type. The only difference, u squared plus 1 with a du at the top, and here it's u squared plus 100. So almost the same with that one. So I'm just going to have you refer to practice quiz problem number 2. And let's look at another one. Number 8. Number 8.
She meant 18.
18.
Yeah, 12 and 18.
Okay. So the integral from 2 to infinity of dx over x plus 2 squared. Alright, now I am going to change this to a limit as t approaches infinity, integral from 2 to t of dx over x plus 2 squared. Okay, and then I'm going to let u equal x plus 2. And then once I do that, this becomes equal to the limit as t approaches infinity. Now these were x equals. Now by the way, du is going to equal, du dx is 1, so du is equal to dx. And this will be u equal 2 plus 2 is 4. When you plug t in, you get t plus 2. And then du over u squared. Now instead of writing it over u squared, let me change it to u to the negative 2. Du. So this integral is equal to, come back over here, limit t approaches infinity, u to the negative 1 over negative 1. The negative sign I can pull out in front. And that's evaluated from 4 to t plus 2. So ignore this limit part and just evaluate this. When I substitute t plus 2 in there, I'm going to get anything to the negative 1 power is 1 over that. So it's 1 over t plus 2 minus, and when I substitute 4 in there, I get 4 to the negative 1, or 1, 4. Okay, and as t goes to infinity, this fraction will go to 0. And this won't do anything, it'll stay the same. And I get a negative of negative 1/4, and I get 1/4, and that's my answer. Okay. Okay. Any questions on 18? Is this all clear?
I got a different answer.
What did you get?
I got 1.
And what did you do different? Where did we part?
I think instead of doing the u substitution, I just took the whole thing and raised it to a negative exponent, and then took the integral of that. And I didn't solve for x plus 2. I just basically did b plus 2. And I didn't take the negative sign out. I distributed it into it, so I got negative 1 over b plus 2 plus 1 over 2 plus 2.
Okay. Yeah, even as one of the characteristics of these integrations, even seemingly easy integrations.
Actually, you know what? I just realized that negative 1 over 2 plus 2 is not 1. That's 1/4.
Okay, so you did get the same thing.
Yeah, I just did an arithmetic error.
And you must have done the u substitution kind of in your head.
Well, I just took the x plus 2 as is because I knew that x plus 2 just was dx if you did the du.
Yeah, you can skip that if you can kind of do that in your head. Yeah. Okay, and let's see what else we got here. It was 18. So we did that, and then number 90 on 8.9. And so this one is area between curves. And this is page 592. Let me go to that. Okay. So R be the region bounded by the graphs. Let me find my magic pen here. Here it is. Bounded by the graphs y equals x to the negative p, y equals x to the negative q. For x greater than 1, where q is larger than p and they're both larger than 1. Find area of R in terms of p and q. Alright, so for me this is just the way that my head works. Is I kind of have to think of it it's kind of like this. Like y equals x to the minus 4 and y equals, now if the x was, if the p was 4, then the q would have to be even larger than that, like 5. Okay, so I'd need a specific number to start to get a feel for this. And then find the area in terms of p and q. Alright, now if I had these two things, and if I had 1 over x to the 4th When it's 1, it's 1. But when it's 2, 1, I get 1/16, really, really small. So 1 over x to the 4th comes down to the x-axis fairly quickly. But 1 over x to the 5th, this is y equals 1 over x to the 5th. 1 over x to the 5th is going to come down even more quickly. It'll be, instead of 1/16, 1/32. It's half as high at the halfway when x is 2. So it's like this. And it goes up quicker over here. Okay, and that one is y equals 1 over x to the 5th. Now, we're finding let R be the region bounded by these two graphs for x greater than or equal to 1. So, we're actually finding the area between these two curves. Let me blow this up. If I make my marks too small, it interprets them too differently. We're trying to find this area between these curves, and it's an infinite. It goes out infinitely far, but it may not be an infinite amount of area. And so the area is equal to the integral from 1 to infinity along the x-axis. This was 1 here. And we need the upper curve minus the lower curve. Now the upper curve is the p1. Like this one. 1 over x to the 4th was the blue, that was the upper. And when you have a higher power in the denominator, it makes it even lower. And if we had these backwards, we'd be getting a negative area. Find the area in terms of P and Q. So we're not going to get an answer like 5 or 7, but we'll get an answer in terms of these letters. Alright, now first thing we have to do is change this into T. Okay, and then this will equal we take the antiderivative of these. Antiderivative of x to the negative p is x to the negative p plus 1 over negative p plus 1. Because p is just some constant like 4 or 5 or something like that. And then minus the antiderivative of x to the negative q is x to the negative q plus 1 over negative q plus 1. Okay, and then we're going to evaluate this from x equals, I'm going to write x equals, all these p's and q's, I'll forget which letter I'm substituting for what, from x equal 1 to x equal t. And then when I substitute t in there, we come down over here. So it's equals limit t approaches infinity. And you can use shortcut notation. If you get tired of writing limit as t approaches infinity, you can say, all right, I'm going to use a script capital L. And script capital L means limit as t approaches infinity, and then you kind of just put that in there every time. You can use whatever shortcut notation that you can make clear. Like that. And then when I put t in, I'm going to get t to that. Now I'm going to write these as 1 minus p. And it's the same as 1 minus p. Minus, I'm going to put t in here, I'm going to get t to the 1 minus q over 1 minus q. That's what I got when I substituted t in. Minus, when I substitute 1 in, I'm going to get, well, 1 to any power is still 1. Over 1 minus q. And now we're going to let t go to infinity. As t goes to infinity, these things are really negative exponents as long as p and q are both bigger than 1. So I want to point that out. These are negative exponents. So as t gets super large, this thing is really in the denominator. It's a negative exponent. And these are going to then drive to 0. So it's going to be, this fraction is going to be going to 0. And this fraction is going to be going to 0 because the t's are negative exponents. Okay. And we're getting some noise. Somebody needs to mute their mic. You just check. So all this stuff disappears.
Did I lock her in there?
We're getting a lot of extra noise. Let me mute somebody who's
Are you staying by yourself?
possibly. Unmute. Okay. I think that takes care of that. So over here, and this, since these all zero out, and these don't have any t's, I'm going to get, distribute that negative sign in there, and I'm going to get negative 1 over 1 minus p. Distribute this negative over here, plus 1 over 1 minus q, which is the same as 1 over 1 minus q, subtract 1 over 1 minus p, and that's my area in terms of p and q. Now, if I went back to my original, for instance, what if p was 4 and q was 5? So, just as to help me understand it, if p was 4, q was 5, then the area is 1 over 1 minus 5 minus 1 over 1 minus 4, which is equal to 1 over negative 4 minus 1 over negative 3, which the second fraction becomes positive, minus the first, and then that's multiplied by 4 over 4, 4 twelfths, multiplied by 3 over 3, 3 twelfths, which would be 1/12. So on that picture that I drew over here, the area, although this goes out infinitely far, the whole area is only 1/12 of the square unit. These two curves are incredibly close together. All right, we will stop here. We're a little over time. The homework is 9.1. Anybody have any questions before I go? All right, I'll stop the video. You all have a great weekend. I'll see you next week.